Hello everyone, I'm very glad to present you today the 13th edition of my publication At a Glance. Today I have the pleasure to present you Tom Lacoma, PhD student at the Institut Parisien de Chimie Moléculaire. He will talk today about his latest article published in ChemMedChem about the impact of chelation on reactivity and cytotoxicity of amylabile biphenyl gold in heterocyclic carbene complexes. So, Tom, the floor is yours.
Thanks for this kind of introduction, Clarisse. So, as you said, I'm very glad to present to you my work on the link between the chelation, speciation, and reactivity and cytotoxicity on Gold-3 complexes in the context of anti-cancer therapy. First, I'll start by a little insight on why we use Gold-3 as an anti-cancer. Historically, it has been thought of an alternative to platinum-2, which cisplatin here is a quite good example, as it is really widespread in the chemotherapeutic arsenal. However, it is widespread, but it has some flaws, which is its huge lack of selectivity, leading to a lot of side effects and also the emergence of resistance. So to overcome this weaknesses of the platinum, Gold-3 has been increasingly studied, where here is the Gold-3 tetrachloro complex. It is square planar as platinum-2, and it has the same electronic structure. However, unlike platinum-2, it is really sensitive to reduction in cellulo, although it would be able to unlock new modes of actions. So to stabilize the gold redox-wise, we have chosen to use cyclometallylated ligands, especially the biphenyl scaffold with the two gold carbon bonds, which are able to stabilize the gold. But the biphenyl pyridine scaffold is also used, and it has the same stability. In both cases, the complexes are able to trigger their toxicity either through a reactive pathway, through the formation of a covalent bond with their target, or through a structural pathway, where this time it's a weak interaction between the whole complex and its target, like this topoisomerase 1 inhibitor. So the whole point of this work is starting from the question, what would happen if we tried to take the best of both worlds and to synthesize a complex that would be both reactive and structural. So to do this, we kept the biphenyl gold scaffold for the stability, and we employ a bridged carbene pyridine ligand, where the carbene is strongly bound to the gold and the pyridine is more labile. So we first synthesized a series of 8 neutral compounds with the open pyridine from the azolium compound and the biphenyl gold chloro scaffold, and we further converted them to the cationic complexes through action of a silver salt. So the syntheses were really smooth and performed in the good yield. And having these 8 pair of complexes, we moved to the biology lab to test for the cytotoxicity. So we were happy to see that all complexes exhibit good cytotoxicity, and it is even increased compared to the previous generation in the name of BGC4, which is the best in class. However, we noticed a few strange things in the results. The first one is that each neutral and each cationic pair has the same toxicity. Moreover, we saw a really mild impact of the substitution of the complexes. We have identified 2 classes of complexes, one most toxic with 2 micromolar toxicity, one least toxic with a 3 micromolar toxicity. However, we have not came up with any rationale behind this. And the last point, which was even more strange, is that the bridged complex 18 and the non-bridged complex BGC0 have the same cytotoxicity, even considering that one is chelate and the other is not. So to come up with answer to all of these questions, we started to study the reactivity and speciation of this pair of complexes, and we noticed that upon addition into the culture medium, which contain chloride and ions, the cationic complexes are able to react, open their metallized cycle, and convert back to the neutral species. So this explains why the neutral and cationic complexes have the same activity, and also why there is a mild impact of the substitution on the cytotoxicity. So having toxic complex is nice, but we wanted to understand what happened in the cell. So we started with what we knew on gold complexes, that some could disrupt the mitochondrial function. We screened for the mitochondrial depolarization for complex BGC19, which is the best-in-class one. And we were really happy to see that it indeed induces a mitochondrial depolarization. So this mitochondrial dysfunction is shortly followed by the entry of the cell in apoptosis, as you can see by the activation of caspase 3 and 7 on this microscopy time-lapse. So all in all, we've synthesized a new generation of gold complexes. Although it is not fully hemilabile in biological media, we have strong proof of the relationship between their structure, their speciation, and most importantly, their activity. And finally, we have the starting of a mechanism of action for these complexes.
Thank you very much, Tom, for this nice presentation. So to anyone watching this on who is interested to participate to this initiative, please don't hesitate to contact us. You have the detail on this last slide.